Okay, so what we are going to do today is talk a little bit about chemistry. Chemistry is everywhere. It's a demonstration that I do on the first day. And it's going to look like this. I'm going to share my screen. And in a second, we will see what's going on here. First of all, we're going to start with the candle. But before we even light the candle, we are going to talk about the chemistry of the matter itself. And what is cool about this demonstration is that it covers 8 main topics that we're going to be talking about this semester right over here, right? So we're going to get to those as we go through. All right, so first of all, let's talk about this candle right here. This candle is made of what? That's right, it's made of wax. And at this time right now, is this wax in the solid, liquid, or gas phase? That's right, it's a solid, right? And what we just called those were states of matter. We just said that the solid, liquid, or gas is the option for the state of matter. So we're going to talk about states of matter this semester. And in the solid state of matter, or the solid phase, we also call it, the molecules are really tightly attracted to each other. That is the characteristic of a solid, is that there are strong attractive forces holding those molecules together in the solid phase. They're really tightly packed together. And so those are 2 things that we're going to be talking about. So one of those we said here, right, was states of matter. And again, those states of matter that we'll talk about are solid, liquid, or gas. And we put them in parentheses because, as we'll see later, that's how we represent the phase or the state of matter in a chemical equation for a chemical or physical reaction, or chemical or physical change, I mean. And we also said that attractive forces are involved in these states of matter, and specifically for a solid, those attractive forces are really strong. Now let's go back. And what happens when we first light the candle? Let's talk about that. When we first light the candle, what do we see happening to the solid wax? Let's see. So we light the candle, and I know you can't see it too well, but I can see eventually, right now, is when the heat from the flame starts to do what to the solid wax? What's that called? When heat disrupts the attractive forces of a solid. Yeah, that's called melting. And so what's happening right now is the heat from the flame is melting the solid wax into a liquid. And so is that a physical or a chemical change? When the wax is changing from solid wax to liquid wax. That, yeah, is a physical change, because the wax isn't changing composition. The wax is just changing phase, or it's changing its state of matter, but it's still wax. And then another thing is happening when the liquid wax gets attracted, right? There's attractive forces from between the liquid wax and the wick. And that's what we call wicking, right? We call it a wick. It's wicking the liquid wax up it via the attractive forces. And then when that liquid wax finally gets hot enough, it vaporizes into the gas phase. And so that, again, from liquid to gas, is that a chemical change or a physical change? Yeah, it's a physical change because it's still wax, it's just getting vaporized into the gas phase. Now, once that gas is vaporized, then that is when combustion or burning happens. That is what is sustaining the flame right now, right? So that combustion or that burning, that is a chemical change. That is when something changes in composition. The actual chemical formulas, as we'll see, change for a combustion. And so this is what we're looking at over here, right? We've got a candle burning on a stir plate, and we'll get to what the stir plate is for in a second. And let's write down those other topics we just mentioned. So we said that physical changes occur. Right? And that is when the state of matter changes, right? We said the solid wax melted into a liquid and then vaporized into a gas, right? We said chemical changes occur in this example as well. So the chemical change in our example for the burning, right, of the candle is combustion, AKA burning, right? And what happens here is the vaporized wax, meaning wax in the gas phase, plus what? What is required for burning to occur? Combustion. What's the other thing, the other reactant for this chemical change? For burning to occur, right, we need oxygen from the air, which is a gas. And we know this is a chemical change because the products are different composition. We don't have wax and oxygen anymore, but we do have carbon dioxide and water vapor, right? And so chemical changes are something that we'll definitely be talking a lot. I mean, chemistry is all about the chemical changes, right? Physical too, but really in the lab, we're going to be doing lots of chemical changes as well, right? And we want to also mention, right, another very important part, the other product, energy. Energy is produced, and that's what we see over here in the flame, right? And so we will have a whole lot of talk about energy this semester, which is involved in every chemical, every physical change all around us, right? So these, right, are gases over here. And we're also going to be talking about gases this semester. We have a whole chapter on gases. And so now the question remains. We want to, since we're scientists, we are chemists, we want to prove that actually, in fact, oxygen is required and that carbon dioxide is a product and water vapor is a product. We can definitely see the energy, right? We can see the flame and we can feel its heat. But right now, we can't tell that oxygen is required as a reactant or carbon dioxide and water vapor are products. So what we're going to do is come back here. And the way that we can do that is now I'm going to take this beaker and I've got some things in it. I've got a stir bar, that's what's spinning right now, so that we can get good mixing of the contents. And this in here is a solution. It's a solution, it's a mixture. It's a mixture of deionized water and a base that is sodium hydroxide. And we're going to talk about acid-base chemistry this semester as well. Right now, how do we describe this mixture, this solution? Right now, what color is it? If you said clear, remember that clear is not a color. Clear tells us something about the clarity. So it is clear and colorless. So from now on in our class, make sure that we're talking when we see something without any color and it's clear, we have to say clear and colorless. But I can make a chemical change occur with this indicator. This is an indicator that tells us that the solution is basic because when I add the indicator to the basic solution, the indicator turns pink. And so that is also an indication that a chemical change has occurred. All right. So what we said we need to do is make sure that we can prove that oxygen gas is required for the chemical combustion to occur, the chemical change, and that carbon dioxide and water vapor are formed. So what we're going to do is place this big beaker right on top. It's a 2-liter beaker. And so we're going to close this system. And let's see what happens. What do we start to see happening over here and on the walls? It's getting a little cloudy, right? What is that, do you think? Yeah, that is the condensation, which tells us that water is produced as a product in this reaction. Ooh, and what just happened to the flame? Right, it went out. So that tells us that oxygen was required for the reaction to occur as well, for the chemical change. And so we're going to keep this going. I'm going to share my screen. We're going to put those up. All right, so I'm going to put on here solutions, because solutions are also going to play a big role in our course this semester. And I'll draw the big beaker that we placed on top of these items with our little beaker, 50 milliliter beaker inside, and our solution. So before any combustion, rather before, in the beginning, right, we saw that the water, H2O, plus a base. What color was it before? Right, it was pink. Oopsie. Right, and we also saw evidence of gases being produced, because from this candle, right, we said that we could see right, water vapor depositing, right, on the walls of the beaker. So that's what I'll draw over here. That water vapor went from gas to a liquid. So is that a chemical or physical change for the water vapor condensing? Right, that is a physical change because it's still water. It just went from gas to liquid, right? And then we also saw that the flame went out, right? So that was evidence of the oxygen gas being required for the reaction, right? And then what did we see happen over here, right, in the small screen to the contents of the solution, right? The indicator went from pink to what? Right, we saw it colorless. Changed to colorless. So that must have meant that a chemical reaction occurred. And I'll tell you what that chemical reaction was. The evidence that we have for the carbon dioxide being produced is the fact that that color change in the solution occurred, because carbon dioxide reacts with the water in the solution to form an acid, right? And this acid neutralizes the base. So this is actually a neutralization reaction or an acid-base reaction. We're going to talk about acid-base chemistry in here this semester. right? So this is how we could tell that the carbon dioxide was produced, right? Okay, so this happens to be a pretty deceptively simple situation that we have going on here, right? There's a lot going on, a lot to think about in such a simple demonstration. Okay, and it turns out that this reaction right here, this whole system that we have going on is actually a model for a real world problem. This is a real world reaction occurring right now in the bodies of water and especially the oceans on this planet called ocean acidification. Okay, so what we just showed over here, right, is what's going on in the oceans where carbon dioxide from fossil fuels is reacting with waters in the oceans to form acid, which is making the oceans more acidic or less basic. So this happens to be a very instructive demonstration, and not only that, but a little model for a big problem. All right, so we're gonna go to the next demonstration, demonstration number 2. And we call demonstrations demos. You'll always hear me talking about demos. All right, so we're gonna stop here and I'll show you the video. Okay. So we're back. And what did we see happen? We saw, right, propane in a balloon react with oxygen from the air. These, by the way, are the reactants in this chemical equation. Right? And these are the products over here. So it's still a combustion. It's another combustion. Right? We still had carbon dioxide and water vapor and energy being produced. Now, the question is, after we saw and heard that combustion, can we say that the energy was released or absorbed? What do you think? Question over here. Was the energy released or absorbed from that combustion? Yeah, released, right? Since we saw it, we heard it, I definitely felt it, we know that the energy was produced as a product, right? So whenever anything is a product, it's been released. Right? So the other question over here is, are the products lower or higher in energy? Right? Are the products lower or higher in energy? All of these over here. Since energy was released, do these products have less energy than the reactants or more energy than the reactants? Are they lower or higher? If you guessed lower, you were correct. Because in order to lose energy as a product, the products that are left over, the chemicals that are left over, the substances, had to lose that energy. the energy had to go out somewhere. So that means that these products here are left over with less energy than the reactants going in. And we're going to talk about that a lot more as we go into our thermochemistry and energy and chemistry chapter. And there you have it. Thank you very much.